In this chapter, we're going to talk about objects moving either through a full circle, so circular motion, or even just a portion of a circle. If you remember, in the definition of acceleration for physics, is some sort of change in velocity in some period of time. And technically, it's the derivative if we want the acceleration at an instant. Since velocity is both how fast an object is moving and in what direction, acceleration relates to changing speed, so speeding up or slowing down, or acceleration also relates to changing the direction. Now, we've been talking about this changing speed up until this point. So we know if the velocity and acceleration are in the same direction, the object speeds up. If velocity and acceleration are in opposite directions, the object slows down. To change an object's direction, so for example, let's say we have something traveling, it has a velocity to the right on the screen here, and it's just traveling along. In order to get it to turn, there needs to be a force. For example, if there was a force, thus an acceleration to the right, and I'm not talking like gravity, just if we were looking down from above and we had been watching this object move to the right, and there was an acceleration that points downwards, that motion, the velocity would turn, and the object would turn. So this is a view from above. When the acceleration is perpendicular to the velocity, the object changes direction. This acceleration, just still due to Newton's second law, this acceleration is caused by some sort of net force. But this acceleration, we call it a centripetal acceleration. This word centripetal means center seeking. The centripetal acceleration always points towards the center of the circle. So the center of the circle the object is moving through. So if we come back up to this picture where we were turning, to continue turning to the right, this acceleration direction would be changing. And it would point always towards the center of that circular path that was being taken by the object. An object does not need to move through a complete circle. Any portion of a circle, the object will have a centripetal acceleration. An object technically can have both a changing direction and a changing speed. We're going to focus mostly on one or the other at this point, just for the simplicity, and that word is a little deceptive. Not that it's per se simple, but just to keep it on the simpler side. So as we're talking about an object moving in a circle, let's say we have a rotating platform. So this is a view from above again. The center of the platform is right there. I'm going to draw a line. Pretend that was nice and straight. If I put two objects on this platform, so it doesn't matter what these objects are, just two small little masses, maybe. And if we get this platform rotating, the rotation rate, we also call this an angular speed. Angular velocity, velocity meaning a direction is associated with it. So here with the arrow I have drawn, I'm implying that this is rotating counterclockwise. The symbol we use to represent this angular speed or rotation rate is the Greek letter omega. SI units are radians per second. Radians, I don't know if you remember, radians is actually a relationship between the radius of a circle and the portion of arc it has passed through. Radians in and of itself is not a true unit, so it is implied, but we could technically write this as 1/seconds. The radians being implied. You will see some problems that give you units in revolutions per minute. You will need to convert those to radians per second. A revolution simply means a full circle. A full circle is 2 pi radians. So we can convert and do the unit conversion to go from revolutions per minute to radians per second. And I'll show you an example of that as we go along. So back to this rotating platform. As this disk rotates, so do the two masses sitting on the platform. At some moment in time later, these two masses are still the same distance from the center as they were to begin with. This inside mass, though, has not traveled, if I call this S1, it has not traveled as far as the outside mass. The outside mass moves through a larger arc, so if it travels a greater distance, then it must have been traveling faster. So if we were to represent the velocity at these moments in time, we would draw these velocity vectors of different lengths. The outside mass would have a larger velocity vector than the inside mass. The inside mass at that moment would be traveling slower than the outside mass. Now, we could draw velocity vectors at any given moment in time. The inside mass, its velocity, will always be smaller than the outside mass. And again, that outside mass has to travel farther, therefore it must need to travel faster. The velocity vector, though, will always be drawn tangent to the circular path that the mass is moving through. Okay. Now again, going back to acceleration, we've been talking about the acceleration involved in changing the speed, speeding an object up or slowing it down. So if I come back to this picture, if either one of these masses is speeding up, they will need an acceleration in the same direction as their velocities. So if it's speeding up or slowing down, the velocity has to be parallel to the acceleration. So we actually refer to this acceleration as a tangential acceleration, because we draw the acceleration vector parallel to the velocity vector, which is tangent to the circular path the object's moving through. The changing direction, though, the masses on the platform, because they are moving in a circle, will always have this centripetal acceleration. To draw that acceleration at any given moment in time, I would draw an arrow pointing towards the center. So the centripetal acceleration always points directly to the center. We're going to use an A sub C or A sub R. C for centripetal, but R for radial. That term is sometimes used because that centripetal acceleration points along the radius, right? The radius of a circle is measured from the center out to the edge. And so the radial acceleration always points inwards along the circle. As an object moves through a circular path, these two masses on the platform will always move through the same angle in here. So even when I originally drew an S1 versus S2, we see that the outside mass travels farther than the inside mass. But if we measure the angle between the lines that those masses are sitting on, that angle is always the same. So we tend to talk about circular motion in terms of the angular quantities, the angle moved through, the angular speed. We'll talk more about these relationships when we get to chapter 12. For now, our main thing we need to be able to work with is understanding and recognizing that an object making a turn, the object could be traveling fully in a circle or just a portion of a circle. That object will always have a centripetal or radial acceleration. And that radial acceleration will be caused by a net force along that radial line. And so that's what we will be looking at. There will be a net force along a radial line, along the radius, and that net force is what's creating that acceleration. For now, our equation that is for the centripetal acceleration, we can write this centripetal acceleration or radial direction two ways. We can write it in terms of the speed at which the object is traveling at, so v squared over r. V being the speed of the object at the moment we're talking about, r being the radius, so how far from the center of the circle the object is. The other way we can write this is in terms of the angular speed. So r is radius still, but here omega is the angular speed or rotation rate. And here the units must be radians per second. in order to get an acceleration in meters per second squared. So again, we'll be looking at net force equals ma. That's the nice thing. We still will draw a free body diagram. It's still forces that we've been using. We have contact forces, field forces, whatever forces are working together to change the velocity in terms of changing direction are the forces that are creating this acceleration. So we'll go through some examples and the approach. Again, watch for the consistent approach, because I will approach problems similarly every time. And that approach will work as you approach the problems as well.